Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we will discuss what catalysts are and how they affect the potential energy diagram, as well as the rate of chemical reaction. Also, we will learn how to quantify the changes in activation energy between catalyzed and uncatalyzed reactions by incorporating the Arrhenius equation. So let's go ahead and get started. Overall, catalysts are substances that increase the rate of chemical reaction without itself being consumed. And so on a potential energy diagram, a catalyst will provide an alternate path as the reaction progresses from reactant to product. And so how might this alternate path look like on a potential energy diagram? So let's go ahead and zoom in on this image. And so I want you guys to notice in red the pathway that the reactants will take if a catalyst is not present. So this is the uncatalyzed reaction. In purple is going to represent the alternate pathway that will be provided by the catalyst if the catalyst is present in the reaction vessel. And so the alternate pathway that catalyst provides is basically a lowering of the activation energy. And so by lowering the activation energy, there's going to be a higher probability that those reactant particles, a higher fraction of those reactant particles, will have enough kinetic energy to overcome this activation barrier. And so there's some more things I want to point out. First and foremost, the only thing that a catalyst does change on a potential energy diagram is the height of the activation energy. And so it decreases the activation energy. However, the potential energy of the reactants and the potential energy of the products remain unaffected. In other words, for both catalyzed and uncatalyzed reactions, the divergence is going to be on the same energy level. And the convergence of catalyzed and uncatalyzed reaction will also be on the same energy level when reactants gets converted into products. And so what's the significance of that? Well, for this exothermic process, this example, so this is an exothermic potential energy diagram, this is telling us that the enthalpy, the change in delta H between reactants and products will still stay the same. And so the delta H, or enthalpy value, is still the same because the potential energy of the reactants and the potential energy of the products will be the same, and it's not altered by the addition or the presence of the catalyst. And so the only thing that the catalyst does is that it decreases the activation energy, thus providing a new and alternate path on a potential energy diagram that the reactants can follow or take. Okay, and so once again, the catalyst usually provides an alternate path by lowering the activation energy. And this enables the potential energy diagram landscape to kind of change. And so for some reactions, it can be a multiple step path. For some reactions, it can be a one-step path. And so overall, a catalyst will participate in the first step of a reaction mechanism. And we'll see that when we talk about reaction mechanisms in the next lecture video. However, since catalysts are not consumed, then that means that the catalyst will be regenerated at a later step. Okay. And so overall, there are two types of catalyst. There's a heterogeneous catalyst and a homogeneous catalyst. And so a heterogeneous catalyst is basically a catalyst that's in a different phase than the reacting species. In other words, if the reacting species is liquid or gaseous in form, then the catalyst could be solid in form, for instance. And so basically the idea is that the catalyst for a heterogeneous catalyst, it just needs to have a different physical state of matter, so solid, liquid, or gas, compared to the reacting species. And so for a solid catalyst that's coming in contact with any liquid or gas phase reaction mixtures, the reactants are typically adsorbed onto the catalyst surface. And so we'll take a look at what it means for a solid or gas reaction mixture to be adsorbed on a solid catalyst in just a second. For a homogeneous catalyst, that's basically just describing to the reader that the catalyst is in the same phase as the reacting species. And so, for example, if the reacting species is aqueous in phase, then the catalyst will also be aqueous in phase. And that allows us to label that catalyst a homogeneous catalyst. All right, so let's go ahead and take a look at an example of a heterogeneous catalyst. And so, for example, we have ethylene, which can be gaseous in state, and hydrogen gas. And so these are the reacting species. And so typically when you guys are trying to incorporate a catalyst in a balanced chemical equation, it's typically written on top of the arrow sign. So platinum would be a catalyst. And so what makes this an example of a heterogeneous catalyst is the fact that platinum is solid in state, whereas H2 gas, or H2 is gaseous in phase, as well as ethylene. And so notice that since there is a difference in physical state of matter between the reacting species and that of the catalyst, it would make the catalyst a heterogeneous catalyst. And so this diagram kind of illustrates the general mechanism. So the green circular spheres here is representing platinum. And so when these gas phase reactants make contact with platinum, they're being adsorbed, meaning they're interacting with the surface of this catalyst, but they're not really becoming part of platinum. An analogy to this is throwing like a gummy bear on a window, right? So you can kind of use that analogy to describe something that's adsorbed. And so the really cool thing about this platinum catalyst is that it fixes the orientation of the hydrogen gas and the ethylene gas such that when these two reactant species collide, the orientation is already correct. And that fixing of the orientation allows the activation energy to decrease. And so once the hydrogen atoms migrate to ethylene, ethane is produced, and this gas molecule will take itself away from the catalyst and becomes its own product. And so you guys actually use heterogeneous catalysts on a daily basis, especially if you drive cars. And so when you when the gas inside an engine combusts, it will produce, for example, carbon monoxide, nitric oxide, and oxygen gas. And so these these particles, these gaseous particles, will pass through a catalytic converter, which is typically present underneath the chassis of your car. And the catalytic converter looks something like this. And so that allows these gas molecules to adsorb itself onto the surface of the metal, allowing carbon dioxide and nitrogen gas to be produced and later released in the atmosphere through the tailpipe. And so an example of a homogeneous catalyst would be, for example, the biological enzymes. And so enzymes in your body perform a lot of the biochemistry that allows catabolic and anabolic reactions to occur. So without these enzymes, it'll take years and years and probably millions of years for your body to break down a burger. And so in the presence of enzymes, that burger can be broken down very quickly, and the nutrients absorbed from the burger can, for example, provide energy in the form of ATP to do cellular work. And so overall, if you have a substrate, so a substrate is the substance that goes into the enzyme. So S for substrate. So for the substrate to be converted into product, it has to overcome the activation energy. And so this is an example of what a potential energy diagram might look like for an uncatalyzed reaction. And so when an enzyme acts on a substrate, it's going to provide an alternate pathway decreasing the activation energy. So this is E for enzyme, S for substrate. So ES represents the enzyme substrate complex. And so since the activation energy is lessened, it allows for the rate of reaction to occur much more quickly to produce the enzyme in the product. And so I'm just going to go ahead and add arrows over here. So E for enzyme, and then S for substrate. And so this ES is the enzyme substrate complex. And then E and P is simply going to be the enzyme and then the product. And so what makes enzymes, biological enzymes, a homogeneous catalyst is because it's in the same phase as the substrate. And so both the enzyme, biological enzyme, and the substrate, it's inside your body, so it's considered aqueous. Okay. All right. And so let's go ahead and discuss the effects of catalysts with respect to the Arrhenius equation. And so first and foremost, the addition of a catalyst causes the rate of the reaction to increase. So in other words, the rate of the catalyzed reaction is much greater than the rate of the uncatalyzed reaction. So those are the take-home points. The rate constant K is going to increase, so the rate constant for the catalyzed reaction is going to be much greater than the rate constant for the uncatalyzed reaction. And the activation energy for a catalyzed reaction is going to be much less than the activation energy for uncatalyzed reaction. And so this is the primary mechanism, if you will, for how catalysts increase the rate of the reaction and thereby increase the rate constant K. And so we can go ahead and quantify the changes in activation energy by incorporating the Arrhenius equation. And we can go ahead and do so by writing the Arrhenius equation for both the catalyzed and uncatalyzed reaction. And so we can say the kcat, or the rate constant for the catalyzed reaction, is equal to the pre-exponential, or not pre-exponential, the frequency factor, times that by the exponential raised to the EA of the catalyzed reaction over RT. And for the uncatalyzed reaction, it's the rate constant for the uncatalyzed is equal to the frequency factor times this by the exponential raised to the activation energy of the uncatalyzed reaction divided by RT. And so what we can do is we can combine them such that we're going to take a ratio. So if we take a ratio of both catalyzed and uncatalyzed reaction, we should be able to create an equation that allows us to quantify the activation energy for either the catalyzed or uncatalyzed reaction. So let's go ahead and go through that proof. And so first, by taking the ratio of the catalyzed and uncatalyzed reaction, we can go ahead and cross out the frequency factor, since they're going to be the same. And so what we get is kcat over k uncat, so uncatalyzed. And that's equal to the exponential raised to the negative EA for the catalyzed reaction over RT over negative EA for the uncatalyzed reaction over RT. And so since the exponential is present, I can go ahead and take the natural log of both sides. Okay. And so I'm just going to copy this real quick. I'm going to duplicate this because I want to be able to show the progress of my steps here. And so I'm just going to erase this for now. Uh-oh. Okay. All right, so if I take the natural log of both sides of the equation, let me see here. I can go ahead and actually simplify this term first. And so by simplifying this term, I get E negative EA of the catalyzed over RT minus parentheses negative EA of the uncatalyzed reaction over RT. So if you guys recall properties of logs, natural logs, etc., if two items are being divided, then you can go ahead and subtract them. Okay, so I'm just simply combining these terms using properties of log, natural log, etc. And so I can go ahead and reduce this even further by distributing this negative, making it into a positive. And so what I'm going to do, since this is a positive value, I'm just going to switch that to the front. So basically I have positive EA of the uncatalyzed reaction, okay, over RT minus, and so I'm basically kind of switching them. This is going to be EA of the catalyzed reaction over RT. Now, if you guys recall rules of subtraction for fractions, if they have the same denominator, then you can go ahead and combine them. And so what you get is the activation energy for an uncatalyzed reaction minus the activation energy for a catalyzed reaction over RT. And remember, this is still being raised to the e power. And then there's that natural log that's in front. Okay. All right. And so what this does is that, actually, let me put this equals to natural log of K cat, the rate constant of the catalyzed reaction, over the rate constant of the uncatalyzed reaction. Okay. And so what this allows us to do is it allows us to cancel the exponential with that of the natural log, leaving us with an equation such that, I'm going to run out of room, the natural log of k cat over k uncat, so uncatalyzed, I am going to run out of room, equals to this whole thing. EA of the uncatalyzed minus EA of the catalyzed over RT. Okay? And so now we have this beautiful equation that if we know, for instance, K cat and K uncatalyzed, and perhaps the activation energy for the uncatalyzed reaction, we can determine what the activation energy is for the catalyzed reaction if we know the temperature, something like that. Okay. All right, so let's go ahead and apply this equation to one problem. So in a hypothetical chemical reaction, the conversion of reactants to products requires an activation energy of 63.8 kilojoules per mole. So when the catalyst was added, so the next sentence infers that this activation energy is for the uncatalyzed reaction. Now when the catalyst was added, the rate of the chemical reaction increased by a factor of 12. So whenever you guys are talking about a factor of 12 or a factor of something, it's referring to a ratio. And so since the ratio is that of the rate of the chemical reaction, it's just basically a ratio of K cat over K uncat. So K cat over K uncat, so uncatalyzed, is 12. And so what we want to do is we want to calculate the activation energy for the catalyzed reaction. Now there is one thing that I forgot to put in here, which is temperature. So just for kicks, let's just say that the temperature is 35.0 degrees Celsius. And so I did forget to type that when I was writing this problem. All right, and so what we're going to do is we're going to use this equation over here, and we're going to plug in all of the pieces and basically solve for the activation energy for the catalyzed reaction. And so the natural log of the rate constant of the catalyzed over the rate constant of the uncatalyzed reaction is equal to the activation energy for the uncatalyzed reaction minus the activation energy for the catalyzed reaction over RT. And so since the ratio is 12, I'm simply going to put 12 for this fraction. So I have the natural log of 12 is equal to, now my activation energy for my uncatalyzed reaction is 63.8 kilojoules per mole. And remember, R is in units of joules per mole, so I'm just going to simply multiply this number by 1,000. So I have 63,800 joules per mole minus the activation energy for the catalyzed reaction, which is unknown and what we're trying to solve for. And I'm going to go ahead and divide this by 8.314 joules per mole Kelvin times this by temperature. And so if we are assuming that this reaction happens at 35 degrees Celsius, I just made it up. So I'm going to add 35 by 273.15. And so this is going to give me 308.15 Kelvin. And so I'm going to go ahead and plug in 308.15 Kelvin down here, allowing the units of Kelvin to cancel. And so it will also allow joules per mole to cancel. Now remember that the activation energy, this term also has units, and it's joules per mole. And so the final units, so to speak, is going to be joules per mole. All right, so I'm going to go ahead and start plugging some things in the calculator. So I'm going to take this 308.15, I'm going to multiply it by 8.314. And so that's going to give me 2.56 2 times 10 to the positive 3. And remember, I canceled a whole bunch of things out, so this number in the denominator becomes unitless. And then I still have that 63,000 over here, and then minus EA catalyzed. And we know that the unit is in joules per mole. And so natural log of 12 is going to be 2.48. So since there are 2 sig figs, that means I have 2 decimal places. So I'm going to take this number and I'm going to multiply it by 2.562 times 10 to the negative 3. So I'm going to multiply that by 2.562 times 10 to the positive 3. And so what I get is going to be 6.37 times 10 to the positive 3 equals to 63,000 minus EA. Okay. And so I'm simply going to subtract both sides by 63,000. And so what I get is going to be negative 5.66 times 10 to the positive 4. And that's going to equal to negative EA of the catalyzed reaction. And last but not least, I'm going to divide both sides by negative 1. And so my final answer, so the activation energy for my catalyzed reaction is going to be 5.66 times 10 to the positive 4 joules per mole. Now, if I wanted to express this in terms of kilojoules per mole, I can go ahead and move this decimal place one time to the right, and that brings that number down to positive 3. And so it's going to be 56.6 kilojoules per mole. All right. And so let's see if our answer makes sense. So the catalyzed reaction is going to be 63.8 kilojoules per mole. However, once we add a catalyst, the activation energy decreases to 56.6 kilojoules per mole. And overall, that decrease is going to give us a factor of 12, an increase in the rate of the reaction by a factor of 12. So that's a lot. Okay, so by decreasing the activation energy, it looks like approximately by 6 or 7 kilojoules, we get an increase of the rate of reaction by a factor of 12. So that's a lot. Okay, and so if you wanted, you can sketch a quick diagram. And so this would be the activation energy for the uncatalyzed reaction. And I actually don't know why I made it exothermic. This problem did not tell me if it's exothermic or endothermic. And so I'm just giving you an example. And so this would be an example of the alternate pathway that a catalyst would provide, such that this height would be 63.8 kilojoules per mole. And this height, the catalyzed reaction, would be 56.6 kilojoules per mole. Okay. So obviously this potential energy diagram is not to scale, but it kind of gives you an idea or visual that the catalyzed reaction will have a lower activation energy than the uncatalyzed reaction. All right, so that's pretty much it for this lecture video. Hopefully you guys have a stronger idea of the power of catalysts in terms of increasing the rate of reaction. And hopefully you guys understand that one mechanism that allows a catalyst to increase the rate of reaction is by decreasing the activation energy. And one way that it can do that is fixing the reactants at a very specific orientation such that it mimics the transition state. So the transfer of, I'm sorry, not so much the transfer, so that the creation of the products can already be reached in a quick fashion. All right, guys, so that's pretty much it for this lecture video. I'll see you in the next lecture video. Bye.